Howdy. So today we're talking about action at a distance. And action at a distance really does happen. You might think that it's only the stuff of Star Wars and it's fictitious, but action at a distance actually happens every day, right? So gravity, that's actually a really trippy thought. The moon is being pulled by the Earth. The sun and the Earth are pulling together. The whole um, solar system and the whole, even the Milky Way galaxy, is whirling in this gravitational field that pulls each other without actually touching them. So gravity is just one example, and we'll talk about that in great detail in this unit. I'll get back to these things in a second. The second example, look at this. I mean, this is kind of a trippy thing you could buy online. It's a floating thing. It's a floating magnet, right? And so magnetism, you can move things without touching them. Anybody that's ever played with the Thomas the Train toy set knows if you switch the trains opposite directions. I think I actually have a Thomas train here somewhere. Where's my Thomas train? Nope, it's gone. I have the track. Here's the track. All right. So if you switch them backwards, they push each other without even touching, right? That's Yoda, man. It's like Yoda stuff. Um, Electricity, man. Static electricity gets in your hair and it pushes the hair apart. So the hair is standing on end, right? So you can definitely have an effect on something without touching it. Electrical forces. Um, Light charges repel, like the two protons, and opposites attract, like the proton and the electron. Um, do those two equations look similar? Just look at the equations themselves. I mean, they look pretty much exactly the same, don't they? I mean, the same format, right? They're both telling how strong a force is that is, in this case, just pulling these two things together. And this is the force of gravity. And this one can either repel or attract, and that's the electric force. And they're actually the same exact basic format of how they're formed. And they're this action at a distance idea where the distance between them is d, and sometimes you'll see this as an r as well, because a radius is very often used with satellite motion, like it's going around the moon is going around the Earth, and so that distance would be a radius. You'll see it written both ways actually, but anyways, these two look familiar. Well, this is the one we're dealing with in this unit, and later on we would deal with this one, but in AP this year, because we're going quicker, um, the College Board said you probably won't get to this, so probably don't even try it. It's not covered on the AP exam. So if we get there, we get there. If we don't, we don't. Anyways, moving on. Both of these have what's called an inverse. Let me see if I can get rid of this thing that I can. Inverse square law. So underneath, both of these have a square underneath the distance. And so what that basically means, and we'll talk about that in a little bit later video, but what that basically means is the farther away you go, the force actually diminishes by the inverse square. So if you're twice as far away, you're not 1/2 as much force. You're actually 1/2 squared, which is 1/4 the force. If you're 3 times farther away from something, you're not 1/3 the force. You're actually 1/9 the force. If you're 5 times away, you're 1/25 the force. It's called the inverse square law. And it's interesting how it works with radiation, sound, illumination, magnetism, electrostatics, and gravity. This is very important if you're at a concert. Boom, 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 and you're next to the speaker. Go twice as far away, and the damage to your ears won't be half as much. It'll be 1/4 as much. Not easy to get far away from your headphones, so you might want to turn the volume down a little bit since you can't get away from it and follow the inverse square law. If you're worried about your cell phone giving you some sort of I don't know, brain cancer or something when you sleep next to it, don't sleep next to it right on your brain. Put it twice. If you put it twice as far away, it'll be 1/4 the risk. Put it another 3 feet away, right? It'll be 1/9 the risk. So the inverse square law is really a practical thing to know. Okay, so intro to the law of gravitation. What is the universal law of gravitation, and does Earth have gravity? So we have two equations now, which is Fg equals mg, which works on the surface of the Earth. It's the same thing as F equals ma, because the a is gravity. But we also have this. The universal law of gravitation works anywhere in the universe, and it's the attraction from any two objects. you have to have two objects to have gravity, which I'll explain in the equation in a moment. So it's not as if the Earth has gravity. The Earth doesn't have this little g. Everything has gravity. In fact, you pull on the Earth. The Earth pulls on you. You pull on the Earth. You actually pull on the Earth just as hard as the Earth pulls on you because the two objects pull each other. You can't have one object pulling the other. The Earth doesn't pull you. You pull each other because of this equation, which I'm going to explain in more detail on the next couple pages. Okay, so here is the equation. Here is the equation, and I'm right in the center now. The ULG, Universal Law of Gravitation. The force of gravity will be equal to, and so it says the force of gravity is the force of gravity between any two objects. The two objects are m1 and m2, and divided by the distance between them squared. G is what's called the universal gravitational constant, and it's the same everywhere in the universe because it's the universal gravitational constant. It's not like the local gravitational constant. It's the universal gravitational constant, and it is a very, very, very small number, 6.67 times 10 to the 11th, right? 10 times 10 to the 11th. That's a very small number, and it works anywhere in the universe, right? 9.8 newtons per kilogram, that works on the surface of the Earth. That equation works on Earth or Earth-sized planets, but this one works between any two objects attracting each other anywhere in the universe. Okay, moving on. Okay, so let's see. These are knowns and unknowns for things that are on Earth. Like, for instance, the gravity of Earth. Well, that's actually pretty easy to find experimentally. You just weigh something. Right? Okay. Yeah. 1 kilogram weighs 9.8 newtons. That's gravity on Earth. That's pretty easy. The acceleration, just drop something. Just drop it. Okay. It's going to accelerate every second. It goes 9.8 meters per second faster. Right? The radius of Earth, ask Magellan. Get in a boat. Go around the Earth. Well, I know it's flat and stuff, but I mean, like if it were spherical, ask Magellan. He went around the Earth, right, and said, "Hey, this is how far it went. This is how long it took. Set your watch." The mass of the Earth. That's a little harder. The mass of the Earth, we're going to stick it on a scale or something like that. Start digging, like, I don't know, put on a balance. Ask Cavendish. Who's that? Capital G, 6.67 times 10 to the 11th. How the heck do we find that? Ask Philip von Jolly. So, all right, so what did von Jolly do? Well, John von Jolly was trying to actually see Newton had already set up the equation that said that the force was proportional to the two masses and inversely proportional to the distance, that part, but he didn't know what big G was. And the reason he didn't know what big G was, oh, by the way, little g is the gravity in a local place. Big G is the gravitational constant, the big universal. Newton couldn't figure it out because how's he going to figure out the mass of the Earth? Now, apparently, some people say that he kind of estimated the mass of the Earth and then estimated G, and apparently he was pretty close, but I haven't corroborated that. So anyway, Newton didn't figure out big G. Newton knew, though, that the two masses were directly proportional. The force and the masses were directly proportional, but inversely proportional to the square of the distance. He knew that part. He didn't know big G. So how do you find big G? It's a giant thing. This is another book, so I forgot to get rid of that. It's another book. Don't worry about that. So what he did is he took a 6-ton lead ball, which is a 1-meter diameter lead ball, and he rolled it underneath a delicately balanced mercury flask. And when he did, the balance actually swayed. It was called a torsion balance, and it actually swayed. So he rolled a 6-ton lead ball like your fishing weight underneath the balance, and it swayed. And when it swayed, he's like, oh my gosh, that's so cool. The lead ball actually had so much mass that it had enough gravity to be detectable, right? You need a massive object, and then also to roll it. It's like 1768 or something like that. It was a long time ago he did this. So anyways, by the deflection, he figured out that he was pretty close to figuring out 6.67 times 10 to the 11th. That's a hard number to figure out because it's so stinking small. Anyways, thank you, Philip von Jolly, for having this, jolly old experiment that found out capital G finally. Okay. Let me give you a real easy example. What is this equation? So if I had two apples out in space, 2 Newton apples of 1 kilogram out in space, how much force would be between them? So I got apple number 1 is mass number 1. I got apple number 2 is mass number 2. I got G, which is 6.67 times 10 to the 11 Newton meter squared over kilogram squared is the units, divided by the distance between them squared. I'm putting them 1 meter, and they're not on Earth, so they're not going to fall. They're sitting out in space. And so you cancel all the units, bada boom, bada bada boom, and you get 6.67 times 10 to the 11 times 10 to the negative 11 newtons. So the basic idea of this, if two 1 kilogram objects are 1 meter apart out in space, the force between them is 6.67 times 10 to the negative 11 newtons, which is a really, really, really small number. It's a very weak force. So compared to like magnetism, oh man, magnetism is super strong compared electromagnetism, super strong compared 10 to the ninth, not 10 to the negative, not 10 to the ninth is magnetism. I mean electromagnetism. This is 10 to the negative 11. That's a lot of zeros, man. So anyways, it's a very weak force. That's why you don't really like consider like, oh, this has gravity, but it does. It just has a very small amount. A 6-ton lead ball has gravity, not so much as the Earth. But the Earth is so big, we really feel its gravity. That's why we think, oh, the Earth has gravity, but I don't. Actually, you do have gravity. A comet has gravity. You know, a rock, anything that has mass has gravity. That's the idea. But in order to have gravitational pull, you have to have two objects. They have to pull each other, right? So you notice it's not like the Earth is in this, but nothing else is. Like this could be the Earth, and this could be you. This could be the Earth, this could be the moon. And by the way, it's not the distance between them. It's the distance between their center of mass. So it's the center of the Earth to the center of the moon. Be careful about that. It's not the surface of the Earth to the surface of the moon. It's not your feet to the floor. That'd be weird, right? There'd be no distance between you, and then the gravitational force would be infinite almost. Okay, it's from your center, like your belly button, to the Earth's belly button, the center of the Earth. Okay, Cavendish. Cavendish actually figured out the weight of the Earth. It's this. This is called weighing the Earth. So he took, since he put this through the thought process. He said, "What if I had a 1 kilogram apple? I'll put that right there, 1 kilogram apple. And what if I know G because of Philip Von Jolly? Thank you. I know G, and I know that a 1 kilogram apple has a weight of 9.8 newtons." Right? And if I know how far it is to the center of the Earth, I can figure that out pretty easily because Magellan went around the Earth and I had the circumference, right? And there's a relationship between the circumference and the radius. So I've never been to the center of the Earth, but I know where it is since it's spherical, not flat. So you put it in, and the only unknown is ME, the mass of the Earth. So really cool. So yeah. So just mentally, once you get that far, you're like, boom, I got it. The mass of the Earth is actually 6 times 10 to the number to the 24th kilogram. Is a lot of kilograms. 6 times 10 to the 24th, 24 zeros. In your calculator, you write it like that, 6E24. There's an EE button on your calculator. Make sure you're using the EE button on your calculator, right? And that's the idea. That's wicked awesome. Okay, moving on, not too much farther. Graphs and proportions. I'm not going to really cover this right now because they're covered in a video that's in the actual quiz itself. So graphs and proportions, it basically just talks about, okay, gravity versus mass, and there's a video right there you can watch. That video is actually on the quiz, and same thing with the next slide. Oops, going to play it. The next slide,
Okay, in this
which is another mathematical relationship: gravity versus distance versus gravity versus mass, right? And so just go for it. Those ones are on the other thing. But anyways, that's where we're at. Go ahead and try to do the good old work on the quiz and see how that goes. All right, let's see if I can stop this video. Nope. Now I can.